The next is chapter number 2, electric potential and capacitance. Electric potential and capacitance. See, chapter number 1 starts with force. Whatever you have studied in chapter number 1, including electric field, that can be derived from force. That electric field was derived from electric force basically. And electric force depends upon electric field. So that chapter 1 revolves around electric force always. Chapter 2 revolves around work done by electric field and work done in electric field. So let's first start with work done in electric field. The whole chapter will revolve around work done. The way chapter 1 revolves around force, electric force. So to calculate electric field, work done in electric field. Let's consider a straight field lines. These are field lines. So this is electric field. In this electric field, we consider 2 points, a point A and a point B. I placed a charge plus Q over it. So electric field will exert an electric force over this charge at A. It will exert a force Fe over charge at A. So the electric force on charge Q, Fe, will be simply QE. This is how we calculate electric force, electric field. Force on a charged particle in electric field. Force on a charged particle simply charge multiplied by electric. So to move this charged particle from A to B, you're supposed to apply an external force. Now you have to move this charged particle from A to B. So to move this charged particle from A to B, let's apply a force, some external force. So the external force to be applied. See, this electric field will push this charged particle in the direction of field. We want to move this charged particle in a direction which is opposite to that of field. To move this particle opposite to that of field, you have to apply an external force. What should be the minimum value of this external force? More than Fe. The external force will be exactly equal to minus of Fe. Means direction of external, this negative sign says that direction of external force is opposite to that of force due to electric field. So this Fe is the electric force on charge Q by electric field. This is force on charge by electric field. The external force that you will apply will be in a direction which is exactly opposite to that of force due to electric field, and the magnitude would be equal. It's a very usual misconception, very common misconception, that if I say that force acting on a charge is zero, if I'm saying that force acting on a body is zero, force acting on a body is zero, that means acceleration is zero. Zero acceleration doesn't mean that body is always at rest. Zero acceleration means that body is moving with a constant velocity. So when I'm writing that F external is equal to Fe, doesn't mean that the charge is at rest. The charge can move from A to B with a uniform velocity. It's actually moving from A to B with a uniform velocity. That's why I'm writing F external is equal to minus of F. If I consider the magnitude of F external, then the magnitude of F external is exactly equal to the magnitude of Fe, which is equal to QE. That's my second equation. Then if I consider, let's consider that field is uniform. Let's consider that field is non-uniform. Let's take a very general case. That field is non-uniform. Here electric field is non-uniform. That means this F external is a variable force. F external is a variable force. See, if this E is non-uniform, if value of field change continuously, then the external force, which depends upon the value of E, will again change. So we can say that force is variable force. Okay, what's the formula for calculating work done? I need work done by external force in carrying charge Q from B to A. Tuba, what is work done? Formula of work done. Work done is dot product of force and displacement. Yes, this is dot product of force and displacement. We use this formula if your force is constant. But if your force is variable, then we use that work done is integral of F dot dr. So in this case, your force is variable. So to calculate work done, we will use this integral. So for work done by external force, we will write this as this is integral of F external dot dr. This is integral of F external dot dr. This is how we write work done by external force. That is F external dot dr. Say this is equation number 3. This value of F external can be substituted from equation number 2. And if I write this in vector form, this is how we write magnitude of F external. If I consider that as a complete vector, then I can write this as minus of QE. This minus sign will show that they're acting in opposite directions. So I can easily substitute 2 in 3. If I substitute 2 in 3, then work done by external forces minus of Q E dot dr. Minus of Q E dot dr. This is how we calculate work done by external torque. And you will integrate it from A to B. You're taking charge from A to B. So this is how we calculate work done by external force in carrying a charge against the field from point A to point B. We will use this expression if your field is variable. Okay. Now, if I consider that this electric field is uniform, if I say that electric field is uniform, if E is uniform, if your electric field is uniform, then you can take this electric field outside this integral. So work done by external force will be simply minus of QE. This Q and E are constant. QE dot integral of dr from A to B. When I'm writing A to B, that means from position vector RA to position vector RB. Position vector of point A to position vector of point B. Afroza, what is the integral of dr? Yes. It's dr, no? Simple dr. If you integrate dr, then the integral of dr is simply r. So work done by external torque is minus of Q E dot. We're integrating dr. See, if you are integrating just dx, we did this thing when we have revised integration and differentiation. Integral of dx is x. Integral of dy is y. If you just have dx and only dy. And if you have only dr, then the integral will be r. The limit is from RA to RB. Fatma, just unmute yourself and substitute limits here. What would be the final result? Fatma.
RB minus RA.
So yeah, it would be RB minus RA. And this is work done from A to B. So remember this thing. If you are taking a charge from point A to B, then this is minus of QE dot RB minus RA. If you're taking from B to A, then it would be RA minus RB. This is work done by external force. What about work done by external field? Can we somehow relate work done by external electric field to the work done by external force? Can we relate work done by electric field with this external force? Okay, just check. What's the relation between electric field and external force? Electric force and external force.
They're equal, they're opposite of each other.
Yeah, they are equal and opposite of each other. That means their work done will differ by a negative sign. If two forces are acting in opposite directions, if their magnitudes are equal but directions are exactly opposite, then their work done will differ by a negative sign. So the work done by electric field, EF, will be exactly negative of work done by external force. So remember this result. So the work done by electric field will be, it's A to B. Instead of this negative sign, you will get a positive sign. Q E dot dr. That's the only difference between work done by electric field and work done by external force. Similarly, if your field is uniform, then you can just simply write this as Q E dot RB minus R. Electric field, let's solve this numerical. Electric field E is equal to 2I cap plus 3J cap Newton per coulomb exists in space. Calculate work done in carrying charge of minus 2 millicoulomb. So your field is uniform. There is no x, y, z or t dependency. This is uniform field. From point A, which is 231 meter, to B, which is 322 meter. So if I'm giving some hints, Point A is given, that means position vector of A is given, which is 2i cap plus 3j cap plus k cap. If B is given, then B's position vector is given. This is 3i cap. We have done this thing in Coulomb's law in vector form. We have done these type of numericals in calculations of Coulomb's law in vector form. Now calculate work done by external force from A to B. Okay. So work done by external forces, it's minus of Q E dot, it's RB minus RA. We're moving from A to B, so that's RB minus RA. So this is simply minus Q. The value of charge is minus 2 millicoulomb. So instead of 2, let's substitute minus 2 into 10 raised to the power minus 3. Then you have electric field. The value of electric field is this, 2i cap plus 3j cap. Dot, next you have RB minus RA. So this is 3i cap plus 2j cap plus 2k cap minus RA. So that's 2i cap plus 3j cap plus k cap. So this is plus 2 into 10 raised to power minus 3. It's 2i cap plus 3j cap dot 3i cap minus 2i cap is I cap. 2j cap minus 3j cap is minus j cap. 2k cap minus k cap is k cap. So this is 2 into 10 raised to power minus 3. If we take dot product, I cap, the coefficient of I cap is 2, the coefficient of I cap is 1 here, so that's 2. We're taking dot product, coefficient of j cap is 3, the coefficient of j cap is minus 1 here, so that is 3 into minus 1. There is no k cap, so you won't consider k cap. So that's 2 into 10 raised to the power minus 3. This is 2 minus 3, so that's minus 1. So that's minus 2 into 10 raised to the power minus 3. Is it clear now? We will first perform the dot product. Then after solving this dot product, we will multiply it with 2 into 10 raised to the power minus 3. If your charge is negative, then take that negative sign. Okay, the next topic is line integral of electric field. Line integral of electric field. So line integral of electric field simply means if you take electric field, this is electric field. See, electric field is a conservative field. Conservative field means if you take a charge from one point to another in this field, let's say this is point A, if I say this is point B, and we are carrying a charge Q from A to B, we can carry this charge Q from A to B through any path. You can take it directly from A to B, or you can take along this path or through this path. So if your field is conservative, then your work done will remain same. Work done will be independent of path. So work done in electric field, work done in electric field is independent of path. Is independent of path. It depends only on initial and final position. It depends only on initial and final position. It depends only on initial and final position. It's absolutely independent of path. It depends only over the initial and final position. Hence, electric field is conservative. Hence, electric field is conservative. This is the definition of conservative field. So if you're saying that a field is conservative, that conservative means your work done will not depend upon path. It will depend only over the initial and the final position, nothing else. So if you're saying that your field is conservative, that means your work done will depend only over initial and final position. If I say this is path 1, this is path 2, this is path 3. For all three paths, your work done will come out to be zero. Work done is absolutely path independent. That means your field is conservative. So the first property of conservative field is work done will not depend upon path. Work done will depend only over initial and final position. There's one more definition of property of conservative field. In electric field, work done in a closed path is zero. Work done in a closed path is zero. So if you're saying that a field is conservative, let's say this is your field. So if you're saying that your field is conservative, say electric field, and this is charge Q. You carry this charge Q from one point to another through this path, and then you bring the charge Q at the same point. So if starting and final points are same, then we say that the path is closed. So if your path is closed, then total work done would be zero. This is another property of conservative field. If you have a conservative field, then the work done in a closed path is always zero. There's one more example like gravity. Gravity is conservative field. So you're taking a charge upwards, then downwards in gravity, net force would be zero. So in a conservative field, net work done is zero. And the formula of work done is minus of Q E dot dr. Now, since we are integrating over a closed path, so we put a closed sign. This closed sign simply means that the path is closed. It's moving in a closed path. This comes out to this. Is it clear up to this point? These two are properties of conservative field. The first property is work done is independent of path. The second property is if you have a closed path, then total work done is. And the expression of work done, this I take from the last section. Next, this charge is usually a constant quantity. We can take this charge outside this integral. So this is minus q, integral of E dot dr is equal to 0. Or you can simply say that E dot dr, I can take this minus q to the right hand side, so it will become 0. And I'm left with just E dot dr. What is E here? What is E here?
Electric field.
E is electric field and dr is small length element. Say that element could be this dr. So if you are integration means you are integrating over the whole loop, over the whole closed loop. So if you are integrating electric field over the closed loop, the net value is 0. This is known as line in mathematically. When you are integrating electric field over the entire loop, we call this quantity as line integral. This is line integral of electric. We call this quantity as line integral. This is line integral of electric field. So for a closed path, line integral is. So Fatma, is it this point is clear, right?
Yes, sir.
I just take this minus q is a constant. I take this constant outside this integral sign, and I'm left with just E dot dr. Then I divide this 0 with this minus q, it comes out to be 0. So we are left with only closed integral of E dot dr is 0. Closed integral of E dot dr is 0 means. Now this E dot dr is a mathematical operation. This mathematical operation means I take a closed loop. This is my closed loop. Electric field exists along this loop. I consider a small element dr of the loop, a very small element dr. I first take the dot product of this E with this dr. And there one dr could be here, one dr could be here, one dr could be here. And I keep on integrating over the entire loop. So if I keep on integrating over the entire loop, then this particular expression is known as line integral of electric field. So line integral, just like addition, subtraction, multiplication, line integral is again an operation. It simply means take dot product of electric field with a length element, small length element, and then integrate it over the entire loop. Once you integrate it over the entire loop, you will get net field as close integral of E dot dr. Or is it clear? Line integral now. It's simply dot product of electric field with length element and then integrate it over the entire space. It's not a physical quantity, it's just a mathematical operation. Like work done, electric field, force, it's not a physical quantity, it's simply a mathematical operation, line integral. And again, this is again a property of conservative field. Like gravity is conservative, gravitational force is conservative. So line integral of gravitational field is again 0. The way electric field is conservative, so line integral of electric field is 0. In the same way, gravity is conservative. So the line integral over the gravitational field over the closed path is again 0. Remember this expression. It's usually a one-marker question that what is line integral of electric? So line integral of electric field over a closed path is always 0. The next is the definition of electric potential. So what was electric field? We did electric field in chapter number 1. Electric field is a space around a charge where its electrical properties exist. Or you can simply say that electric field is a parameter which defines electrical properties around a charge. Electric field is just a mathematical parameter which defines electrical properties around a charge. But that parameter is vector. Electric field is a vector quantity. Instead of electric field, to define electrical properties around the charge in scalar form, you can use another quantity which is known as electric potential. So electric potential define electrical properties around the charge in scalar form. It's not a vector quantity, it's a scalar quantity. Just like electric field, it also defines that electric field around the charge. There are electric field properties around the charge. But electric field was a vector, electric potential is a scalar. So you have a charge q. If I say that over this point electric field do exist, if electric field exists, that means electrical properties exist. That means potential will also exist over the same. That's potential. The exact mathematical definition of potential is, there's one more thing. Electric field is property of at least one charges or more than one charge. Can a single charge generate electric field, or to generate electric field you need at least two charges?
At least two.
At least two charges. So electric field is property of, no. To field you need a single charge. To generate electric field you would need a single charge. Property of a single charge. Force is property of two charges. So if you have a single charge Q, it will generate its electric field. But to experience force, you need another charge. So electric field is property of single charge. Just like electric field, electric potential is property of single charge. Electric potential is property of single charge. Is property of single charge. Just like field is property of a single charge, potential is property of single charge. The next is the exact mathematical definition of potential. So you have a charge Q, and you're supposed to calculate potential over this point. So this is charge Q. You're supposed to calculate potential at P due to this charge. So to calculate potential P over this point, potential of capital Q, we consider a reference point which is infinity. We take a charge of Q value. Then we calculate work done to bring this charge Q from infinity to P. See again, we are supposed to calculate potential at P due to charge Q. To calculate this potential, we choose a reference point infinity. We consider a charge Q, which is known as test charge Q over infinity. We calculated work done in carrying this test charge Q from infinity to point P. Let's say this is work done from infinity to P in carrying test charge. The ratio of this work done and test charge is the potential at point P, where Vp is potential of Q at P. This is how we calculate potential at any point. If you want to calculate potential over this point, then consider a reference point which is usually infinity. Take a test charge, calculate work done in carrying that test charge from infinity to point P. That work done gets stored in the system in the form of potential. The next is, if I consider this test charge to be of 1 coulomb, if I say that my test charge is of 1 coulomb, if I substitute Q equal to 1, then you can say that work done from infinity to P by 1 is equal to potential. So we can define potential from this last equation, that electric potential at a point, this chapter number 2 is the toughest chapter of this syllabus. It's very lengthy, it's the toughest one. Electric potential at a point is work done in carrying charge Q, in carrying a unit positive test charge, from one point to another, or it's from infinity to that point, against the electric field, without acceleration. So this is how we define potential at a point. Work done in carrying a unit positive test charge from infinity to a point against the field without acceleration. This without acceleration is important. If your charge accelerates, then along with potential, it will generate electromagnetic waves. It will generate electromagnetic waves, just like light waves. An accelerated charge is source of light waves, electromagnetic waves. So just to avoid electromagnetic waves, we consider that charge is moving without any acceleration. I'm repeating it again, if you consider the acceleration of charge, then problem will become complicated. You will have to consider the electromagnetic waves as well. Next, since we are connecting potential with work done, so this potential is a scalar. Its SI unit is, it's work done by charge. Its SI unit is joule per, or this joule per coulomb could be written as well. The SI unit is joule per coulomb also. This is the SI unit. Okay, the next topic is electric potential due to a point charge. The next is electric potential. Electric potential due to a point charge. Electric potential due to a point charge. So you have a point charge. You're supposed to calculate potential due to this point charge at a separation R over this point. So to calculate this potential, this is infinity. We consider a charge of 1 coulomb at infinity. We have to calculate the work done in carrying this charge of 1 coulomb from infinity to P. And that work done gets stored in the system in the form of potential. So to calculate that work done, I consider 2 points, a point C and point D, having a separation dx. We consider 2 points C and D having separation dx. And this point C is at a separation x from the charge. First, I place this 1 coulomb charge at C. First of all, we will calculate work done from C to D. Then we will integrate it from infinity to R. And this is dx. So consider charge of 1 coulomb at C. That is at a separation x from Q. At a separation x from Q. Force on 1 coulomb due to capital Q. Electric force on 1 coulomb due to capital Q. So Fatma, what should be the magnitude of electric force on this 1 coulomb charge due to this capital Q? The separation between them is x. Both are point charges. You can use Coulomb's law. Fatma, no need to type
1 by 4 pi epsilon 0.
It's 1 over 4 pi epsilon naught. So that's Q.
Coulomb by x square.
The direction of this force, it will act on this charge the right hand side direction or the left hand side. It's a positive charge. The direction of force on this 1 coulomb charge, right or left? This would be the direction of force. The direction of force would be to the right hand side. This capital Q will push this 1 coulomb charge. So this 1 coulomb charge will move to the right hand side. This is the direction of force. So to move this charge from C to D, we have to apply an external force exactly in opposite direction. So the external force to be applied on 1 coulomb charge. The direction of external force is opposite to that of electric force, and their magnitudes are equal. So two equal and opposite forces are acting over it. I consider this as equation number 2. Since both have equal magnitude, so I can write that F external, the magnitude of X external, is just Q by 4 pi epsilon naught x square. That is equation number 3. Then we need work done in carrying this charge from C to D. Tuba, what should be the expression of work done in carrying this charge of 1 coulomb from C to D? Work done in carrying 1 coulomb charge from C to D. Yes, Tuba. Work done, yes, work will be simply the dot product of external force dot dx. This R is acting to the right hand side direction. So all position vectors are acting to the right hand side direction. Even this dx is acting in the right hand side direction. So dx is acting to the right, F external is acting to the left. So the angle between them is 180. So you can write your dw as F external dx cos 180. So your dw is minus of F external into dx. That is equation number 4. So this is the work done in carrying charge from C to D now. Fatma, how would you calculate work done from infinity to P? I mean work done in carrying this +1 coulomb charge from infinity to this point. Padma, how would you calculate this work done from infinity to P?
Closed integral infinity.
F external dx, right? You just integrate this thing from infinity to P, the position vector of P, not closed integral. I'm not calculating work over a closed path. I'm calculating work done from infinity to P. So you will integrate it from infinity to P. The position vector of infinity is infinite and that of P is R. So I'm integrating it from infinity to R. That is equation number 5. Now we can substitute the value of F external from this equation number 3. We can substitute 3 and 5. When we substitute 3 and 5, this will be infinity to R minus of Q over 4 pi epsilon naught x squared multiplied by d. Next, you can take this Q by 4 pi epsilon naught as constant. This is minus Q over 4 pi epsilon naught is constant from infinity to R dx over x squared. So the work done is, it's minus of Q by 4 pi epsilon naught. 1 by x squared could be written as x to the power minus 2 dx. Limit is from infinity to R. So it's minus over of Q by 4 pi epsilon naught. It's x to the power minus 2 plus 1 divided by minus 2 plus 1, and the limit is from infinity to R. So you can write this as, this is minus Q by 4 pi epsilon naught. This is x to the power minus 1 by minus 1. Limit is from infinity to R. So this W is Q by 4 pi epsilon naught. This x to the power minus 1 could be written as 1 by x, and the limit is from infinity to R. So work done is simply, it's Q over 4 pi epsilon naught. Instead of x, substitute R, so that's 1 by R minus 1 by infinity. 1 by infinity is 0, so your work done comes out to be, it's Q over 4 pi epsilon naught. This work done gets stored in the system in the form of potential. Next, this work done gets stored in system in form of potential. I can simply write this work done is potential of charge Q. So the potential of charge Q is simply Q over 4 pi epsilon naught. So this is how we calculate potential. The potential goes as 1 by R. And our field varies with R. Our electric field of a point charge varies with R. Potential varies as 1 by R. What about electric field? Our field varies with R. For a point charge, electric field varies as 1 by R square. But potential varies as 1 by R. For a point charge, the expression of field was Q by 4 pi epsilon naught R square. But for potential, this is just R. So V varies as 1 by R. One more thing. If your charge is negative, then potential would be negative. So you can simply write this as minus Q over 4 pi epsilon naught. If your charge is negative, that means potential is negative. It's minus Q by 4 pi epsilon naught. So for a positive charge, your potential is positive. If your charge is negative, then your potential would be negative. If I plot V versus R graph, then your shape will be hyperbolic. If I consider V versus R graph, then shape would be hyperbolic. Yes, Fatma, potential is scalar, right? Potential is scalar quantity. That's why I'm putting the negative sign in the magnitude. Otherwise, for vectors, magnitude is positive. Negative sign take care of directions. So this is V versus R graph for potential of a point charge. A very basic question. So you have a charge of 3 millicoulomb, rather minus 3 millicoulomb, is placed at separation of 9 mm from point P. Calculate potential at P. This is a straight formula based numerical. Calculate potential at P. Solve it. Further, the potential, the expression of potential for the point charge is Q by 4 pi epsilon naught r. The value of Q is minus 3 millicoulomb, which is minus 3 into 10 raised to the power minus 3 coulomb. The separation is 9 mm, which is 9 into 10 raised to the power minus 3 meter. And 1 over 4 pi epsilon naught is 9 into 10 raised power 9. If I substitute these values, this comes out to be Q, which is minus 3 into 10 raised power minus 3. 1 over 4 pi epsilon naught is 9 into 10 raised power 9, divided by R, which is 9 into 10 raised power minus. This gets cancelled out. 9 will cancel this 9. V is minus 3 into 10 raised power 9. There's one more type of question, very simple question. So let's have you have first write down the formula. So let's you have 2 points, a point A and a point B. Potential at A is VA, potential at B is VB. You have a charge Q. You're supposed to calculate work done in carrying this charge Q from A to B. Work done in carrying charge Q from A to B. Work done by external force. Then this work done is simply charge multiplied by potential at B minus potential at. This is how we calculate work done in carrying a charge from one point to another. For example, let's say you have this point A having potential of 10 volt. Then you have another point B having potential of 20 volt. You have to carry a 2 coulomb charge from A to B. You need work done by external force in carrying 2 coulomb charge from A to B. So work done from A to B is Q, potential at B minus potential. So Q is 2 coulomb, potential at B is 20, potential at A is 10, so that is 20. So you can also calculate work done in terms of potential. Earlier we did work done in terms of electric field. But now this is work done in terms of potential. Simple. Charge, final potential minus initial potential. That's it. This is how we calculate work done in terms of potential.